Okay, in today's lecture, we're gonna actually extend the definition of S measurable function to functions taking values in minus infinity to infinity. So we have extended real number set, extended real number. So extended real number is nothing but we include minus infinity to infinity. Okay, so the function that takes value minus infinity and infinity. So then we have a definition. Okay, so we have a definition, and definition is actually measurable function, but in case of extended real number set, measurable function. Okay, so measurable function, we will say that, okay, so suppose underlying algebra is sigma algebra and we have a measurable space, is a measurable space. Okay, so a function f from x to extended real number set now, okay, is S measurable if f inverse of b belong to sigma algebra for every Borel set b in extended real number set. Okay, so that is what we have when we talk about the measurable function in the extended real number set. Okay, so now we know that we do have a condition for measurable function, condition for m function. Okay, m function means measurable function. Okay, so what is the condition? Again, we will say that suppose access is m space means measurable space. Okay, so and we have a function from x to extended real number set, then f is measurable, if f inverse of a to infinity. Now this a infinity is in the interval. Okay, so this belong to S for all a is in R. Then we will say that f is S measurable function. So that's the condition. Okay, so now we can just go ahead and we can uh, prove a simple proposition. So proposition says, now proposition is very important. We say that, okay, so xs is a measure space, suppose. Okay, and let f1 f2 up to so on is a sequence of s measurable function. Okay, measurable. So we have a sequence of measurable functions from x to extended real number set. Okay, then we define h of x. This is nothing but this is sup of f of k of x, where definitely k belong to z plus. So then the h we define is as measurable. Okay, is as measurable. So the proof is like very easy. So what we need to show h is as measurable. So we will say that let a belong to R. Then if you want to show that h is measurable function, so h is measurable means h inverse of a to infinity is in sigma algebra, right? So now what we can talk about, okay, so this h inverse a to infinity, what is this? So sorry, so what is this? Okay, so we know what is this. Okay, so we know what is this. This means that the elements of x such that h of x belong to a to infinity. Okay, and moreover this is nothing but x such that h of x is greater than a. Now if h of x is greater than a, what is h of x? H of x is nothing but soup. Okay, so we can say that this is nothing, so x belong to x such that h of x is nothing but it is soup of, actually soup of f of k of x, right? And this is greater than a. So now if soup is greater than a, we can say that there exists k, okay, belong to z plus, so such that f of k of x is greater than a. Okay, so such that f of k of x is greater than a. Now if there is one k where f of x is greater than a, what we can say, okay, then this means that the union of all those functions will also be greater than a. Okay, so over here I can say that union of k is equal to like maybe 1 to infinity fk of x is greater than a. This is nothing but this is union of k is equal to 1 up to infinity fk inverse a to infinity. So now we know that each f of k is measurable, and we know that union of measurable function is measurable, so this means that this is measurable, so this belongs to S. Hence our h is measurable. So also we can clearly see that, okay, h inverse of a to infinity is nothing but this is union of k is equal to 1 up to infinity f of k inverse a to infinity. Okay, and since each fk is measurable, so this union of measurable function is measurable, so this means that the whole is measurable, so this belongs to S. Hence we show that, okay, this is measurable function. Now using this result we can say that okay, so if we define now g of x, so my g of x, I define it is the infimum, okay, f of k of x, so is also measurable, okay. So proof is very easy because we already show that k is measurable, so we can write down, we know that g of x and infimum is equal to minus soup of minus f of k of x such that k belong to z plus. Okay, so then we show that now soup of, we already show that soup is measurable, so this means that gx is, since soup of minus f of k of x where x belong to z plus is measurable, hence g is measurable. Okay, so that was the simple proof, so that how soup and infimum of measurable function is measurable, and we just saw it. So if you have any question, you can ask in the comments.